All right, let's get started for today. These announcements are the same as last time, so just a reminder, your project 3 is due tomorrow, and your midterm 1 will be on Monday. There will be no lecture on Tuesday. And your practice midterm, if you want to do it, is due Saturday at midnight. Any questions about logistics? Over there.
Is there discussion next week?
Is there discussion next week? Next week there will be no discussion. Any other questions about logistics? All right, let's get started then. Topic for today is our second lecture on base nets, and we'll start looking at independence in more detail as we can read it off from the graphs. Excuse me, the 3 students over there. It's hard for me to concentrate when there's a lot of chatting going on. Thank you. So, probability recap. What have we seen so far in probability? We've seen the concept of conditional probability, which per definition says that the conditional probability of x given y is equal to the joint of x and y divided by the marginal of just y. This is just a definition. Nothing we can prove here, that's what we start from. Now, with that in place, we can multiply both sides by py, we get the product rule, which says that if we have a joint between two variables x and y, we can decompose it as the conditional of x given y times the marginal for y. We can also swap the roles of x and y, of course. This is all symmetric. We can generalize this. This is called the chain rule, and where we decompose a distribution over n variables as a product of the marginal of the first one, conditional of the second one given the first one, and then keep multiplying with conditional of the next variable given all the preceding variables. And the important thing here to keep in mind that this here, the chain rule always holds true. We're making no assumptions about the distribution over x1 through xn. Any distribution you give over n random variables, you can write it out this way. In fact, you can write it out this way in n factorial different ways, because any ordering of your variables will result in a different way of writing this out. Now, x and y are independent if and only if the following holds true, and this has to be true for all values x and y can take on, that the joint is equal to the product of the marginals. We also saw that that might be a strong assumption to make, and then in practice the assumption we'll mainly be working with is conditional independence. X and y are conditionally independent given z, even only if the following holds true. And keep in mind the analogy here between these two. The only difference here is the conditioning on z everywhere. Okay. X and y conditionally independent given z means that the joint given z is equal to the product of the individual conditionals. There are alternative ways of writing this, such as the conditional of x given z and y is the same as the conditional for x given just z. Similarly for y, the conditional for y given z and x is the same as the conditional for y just given z. What it's saying here is that once you know z, y doesn't tell you anything new about x, and similarly x doesn't tell you anything new about y. Okay, this was our notation, and we'll see a lot of this throughout lecture today. What was a base net? A base net was a way to encode a probabilistic model, meaning a full joint distribution, but without specifying the full joint distribution table. Instead, we specified something more succinct. Okay, so we had a graph, and then we specified conditional probabilities for each node in the graph, and this typically will be a lot more succinct than specifying the full joint distribution. Questions we can ask about a base net are the same questions we can ask about a full joint distribution. What is the answer to some conditional probability query? We can ask other questions. Given a graph, what kind of distributions are compatible with that base net graph? That's the kind of question we'll answer today. This is important for modeling because if you're going to model a real-world phenomenon, you put down your BaseNet graph, you're making assumptions, which we saw last time, but today we'll see we make even more assumptions than we talked about last time. And understanding those assumptions is important to make sure that your model still captures what you think is relevant about the real world for whatever problem you're trying to solve. Okay, so BaseNet semantics formally, for a BaseNet you needed a directed acyclic graph, which means a directed graph means every edge has an arrow on it, only one arrow. Now, in that graph, if you follow the direction of the arrows, you can never traverse a circle. That's what it means to be a directed acyclic graph. Doesn't mean it has to be a tree. There are directed acyclic graphs, like for example, a graph that looks like this. That's a directed acyclic graph. If you ignore the direction of the arrows, there's a cycle, but if you're only allowed to follow the direction of the arrows, you cannot traverse a cycle. So this is a DAG, and there are many DAGs that are not trees, but have these kind of loops in them, but they're not directed cycles. Each node has a conditional probability table for that variable given its parents. Now, while we initially talked about BaseNets in terms of here's a causal process or a noisy causal process that we might want to encode, and we can reflect that process in how we draw the graph, formally what we're saying is that we're encoding the full joint as a product of conditionals, and the assumption we're making here by doing so is the assumption that a node is independent of preceding variables in the ordering, except for its parents, given its parents, right? Because we know that this, if instead of parents here, we had x1 through xi minus 1, this would always be true, because that would just be the chain rule. But by replacing the conditioning on x1 through xi minus 1 by just the parents, we made an assumption. An assumption that helps us representationally, because now the table will become smaller. The less we condition on, the smaller the table. But nevertheless, it's an assumption we make, and we need to understand what it means. It's a conditional independence assumption of this variable, given its parents, from its other predecessors. Okay, so here is an example BaseNet, the alarm network. It's a directed acyclic graph. There are conditional probability tables for each node. And if we want to recover any entry in the full joint distribution, all we need to do is grab the corresponding entries from these tables. So here we have an entry in the full joint distribution, full instantiation of all 5 variables. To compute that probability, we multiply together the corresponding entry from each of those tables. So we grab the corresponding entry, there will be one corresponding entry in each table, multiply those together, and we get the value for the full joint distribution entry. So we can always recover the full joint distribution once we have the BaseNet. Of course, we prefer not to in practice, because the reason we work with BaseNets is to avoid having to deal with full joint distributions. But conceptually, it's important to understand that it always exists, and you can in principle always recover it. Okay, so what's the size of a BaseNet? We've been talking a lot about we want to avoid representing the full joint distribution. The reason was because it's big. So let's compare the size of a BaseNet with the size of a full joint distribution. So full joint distribution over n Boolean variables. How large? Well, we need an entry for every possible instantiation of all variables. So that would be 2 to the n entries in that table. How big is a n-node BaseNet if nodes can have at most k parents? So let's think about this. Each node will have a conditional distribution. And now we're going to try to bound the size of the conditional distribution for each node. So we'll have at most n times whatever the maximum size of a conditional distribution is when there are at most k parents. Okay, how big is a distribution, conditional distribution, when your variable has k parents? Over there. 2 to the k plus 1. Why? You need an entry in that table for every possible joint instantiation of all the variables you're conditioning on, which are k variables, as well as your current variable that you're providing the conditional distribution for. So that's a total of k plus 1 variables that you're considering in that table. And so we have 2 to the k plus 1 entries in that conditional distribution table. If we go back to the example here, you can see that's true here. We had only one variable here, just e, 2 to the 1. Here we had two variables, a and m, 2 to the 2, 4 entries. Here we had 3 variables, 1 up front always, in this case 2 in the back, 3 total, 2 to the 3 entries, which gives us this table here. Okay, so the big difference here is that n is in the exponent over here, but it's appearing linearly in the second expression. So by using base nets, we can represent distributions over large numbers of variables with our representation scaling linearly in the number of variables. Now, of course, the question remains, what's this k here, right? Because it's still exponentially in k. And so what that's telling us, if we want to have a reasonably small representation in terms of what we need to store in memory and so forth, we need to keep k relatively small. And so what that means is, if we want a compact representation of a full joint distribution, we need to represent it with a base net where each node has a relatively small number of parents. Note that it doesn't say anything about the number of children a node can have. That doesn't appear in this equation. A node could have many, many children. It doesn't directly affect this equation. Now, of course, if you have many children, many nodes have many children, then some nodes will have many parents because those arrows need to go somewhere. But the specific thing that matters most is which node has the most parents of all your nodes, and keep that maximum number of parents small. Whereas the maximum number of children any node has is not relevant to this equation here. Any questions about this? Okay, so whether you start with a full joint or with the base net, you always have the ability to compute any full joint probability. But the base net provides huge savings in terms of representation. It's often easier to come up with the numbers. If you need to come up with the numbers for a full joint table, even just the alarm network here, this would be a table with 2 to the 5 entries if you wanted to specify the full joint distribution. And you'd have to say, what's the probability of burglary and earthquake and alarm and John calls and Mary calls, which might be a much more difficult probability to specify than the types of probabilities you have to specify in this base net, where you can think of the variables individually and how they interact with their causes in this case. We'll also see next lecture and the lecture thereafter how it will be easier, at least often, to efficiently answer probabilistic inference queries when you start with a base net compared to when you start with a full joint distribution. Okay, so we've seen what a base net represents, what it's defined as. Now we're going to look at, for the remainder of this lecture, what are some of the implicit assumptions we're making. Additional conditional independencies that will be true for the distribution that we're working with that are different from this thing we've already talked about a node being independent of its predecessors except for its parents, given its parents. And it's important to understand those because they will be present once you draw your base net, and you don't want to make assumptions that are not a good match with the real world. Okay, so as a reminder, independence was defined this way, and we denote it as follows. Conditional independence is defined this way over here, and this is our notation for it. And our canonical example was alarm is independent of fire given smoke because the alarm triggers on smoke, and so once you know there is smoke, it doesn't matter anymore whether fire or something else caused that smoke, the alarm will be triggered very likely either way. Okay, so now what assumptions are we making when we define a base net distribution? So when we specify the base net, this thing here is the main thing we're assuming. For each node, we make an assumption it being independent of its predecessors minus its parents given its parents. This we can think of as the conditional independence assumptions we make because we started from the chain rule, which is always applicable, and then inserted just conditionals given the parents, and that's exactly what we did by inserting the right-hand side as a substitute for the left-hand side, and that's there. But the question now is, are there other independencies or conditional independencies that are guaranteed to be true, that effectively are implied by making these assumptions, and hopefully that we can read off from just looking at the graph without ever having to do calculation with specific numbers and so forth? Was a question somewhere? Yes?
Just to make sure, the current x values are just the subset of x1 to y1 is 1.
Correct. The parents always have to be a subset of x1 through xi minus 1. Otherwise, the derivation that we have made doesn't hold true. So once you specify your graph, which is directed acyclic graph, there will be at least one and often multiple linearizations, meaning multiple orderings, and at least one, but often multiple orderings of your variables that are consistent with the directed acyclic graph. Meaning that if you pick an ordering that's consistent with your graph, that means that you can step through that ordering, and whenever you're looking at a variable in that ordering, things that come before the ordering come somewhere before that variable in the graph. Now, thanks to picking an ordering that's consistent with what we took for our graph, after we apply the chain rule, we can then make this substitution here, which corresponds to a very specific assumption we're making, a very specific conditional independence assumption. We can substitute that in, and we still have an expression for the full joint distribution. We just now made an assumption about conditional independence that's encoded here. So what we're trying to get at now is additional independencies that might be present. So let's look at a first example. Here's a simple BaseNet, 4 variables. Let's first look at the conditional independencies that are true just because of the way we define BaseNets. Okay? For that, we just step through the variables one by one. For x, are there any particular conditional independencies that we assumed? No, because x is the first variable, so we didn't need to make any assumptions there to get the BaseNet joint distribution to work out. Y, the parents of y, so the things we're looking at, do we ever have something where p xi given x1 through xi minus 1 equal to xi given the parents of xi, whether ever this parent set is smaller than the predecessor set. So where is that happening? It's not happening for x. It's not happening for y. Is it happening for z? Yes, for z it's happening because the parent set of z is just y, but the predecessors are x and y. So we are making a conditional independence assumption once we consider the conditional distribution for z. The assumption we're making is z independent of x given y. Moving on, for w, there are 3 predecessors, x, y, and z. We only have one parent, z, so we are making the conditional independence assumption w independent of z given x and y. So those 2 are the assumptions we're making when we go from the chain rule to substituting in the conditional of the variable given its parents. Now the question is, can you come up with another conditional independence that is true among these variables that I haven't written down yet, but that nevertheless is guaranteed to be true? I'll tell you there is one. The question is, can you find which it is? Over there. The suggestion was w independent of x given y. Well, what's the intuition here? The intuition is that we think of this as a causal process. We know that's not really what it is, but it encodes a lot of the intuition often. And once you know y, having information about x will not tell you anything anymore about what w might be, because y is essentially blocking whatever was relevant about x to influence w, because once you know y, that summarizes everything that matters over there.
For the assumption that you assumptions that you wrote down, should it be w being independent from x and y?
Oh, good point. That wasn't written down correctly. Let me swap these two here. So w is independent of x and y given z. Thank you very much. Over here.
So in this example, is that the linearization of the basenet, or is that the basenet itself?
This is the basenet. It also happens to be the linearization of the basenet, because it's a basenet where there's only one linearization. So we have this thing over here. Intuitively, we think this is true. Have we proven this? No, we haven't, right? These ones here we know are true. That's just how we define the basenet. By definition of how we define distribution of a basenet, we know that's the assumption we made. This one here, let's see if we can prove it, okay? So what do we need to show? We need to show that the probability for w given x and y is equal to the probability for w given just y. We don't know yet if this is true. We have a hunch. Let's try to prove it, okay? So let's start with the left side. That's equal to the join between x, y, and w divided by the probability of x and y. Okay. What can we do next? Well, we somehow want to use the fact that this distribution is not just an arbitrary distribution, but one defined by this basenet. So we need to insert that assumption in here. So we're going to work that into our derivation here. We have this is equal to sum over z px y zw over px comma y. All right. Now we have all four variables at the top. We can now expand this using what we know from our basenet is equal to this full joint, which is we have sum over z px times py given x times pz given y times pw given z. Okay. Then at the bottom, what do we have there? At the bottom we have the joint between x and y. We know that the joint between two variables can always be written as px times py given x, so let's just do that here. Now we can start simplifying. This here matches up with this here, then the y given x matches up with this, and so we're left with sum over z pz given y pw given z. Okay, that's our left-hand side. Now let's see what our right-hand side is like. Hopefully we get the same thing. So pw given y, let's do that over here, is equal to sum over z pw comma z given y. This is always true. You can always, if you have a probability or a conditional probability, add a variable up front and sum over it. Okay, nothing to do with basenets, just standard probability. Once we've done this, let's start looking at what we can do that re-expresses this. So now we can write this as sum over z. The conditional of two variables given a third variable can always be written using nothing about the basenet again as just the conditional of one of them given that variable y times in the probability of the other one w given both z and y. Now looking at the basenet, we know that the probability for w given z and y is the same as the probability of w given just z. So we can actually get rid of the y over here. And now we see both of these expressions are matched up, and we have just shown that indeed W is independent of X given Y. Took a bit of work, but that's a proof that indeed what we intuitively thought was true is indeed true. Now the goal for the remainder of this lecture is to build a formalism such that things that look intuitively right to us by just looking at the graph can be directly justified by looking at the graph. So we'll be able to prove things like W independent of X given Y by just looking at the graph without having to expand this into a computation like this. Okay, so question we're after is what independencies might be true. If an independence is true, then you can prove this using algebra. That can be pretty tedious. We did it on the previous slide. That was just a base net with 4 variables. You can imagine with many more variables, it's going to get a lot more tedious, and it was already annoying. If an independence or conditional independence is not true, that you might think is true, the way to prove it's not true is just show a counterexample. You could say, well, here's a counterexample of Y, just one entry, so to say, one instantiation of all those variables involved, showing that the independence is not true. So let's look at the example x, y, z. Are x and z necessarily independent? Well, no, they're not. They don't have to be independent if the base net looks like this, because I can define a base net where has a very special set of distributions where y is always equal to x and z is always equal to y, and as a consequence z is always equal to x, and then x and z are clearly not independent. And so I just showed that when you give me this graph, it's not necessarily true. In fact, in general, it will not be true that x and z are independent. Okay, so here's sometimes you want to think of a story behind it to make it easier to come up with that example. But ultimately, all you need is just something that shows this is not necessarily true. Okay, could they be independent? If somebody gives you a base net shown over here, which is an incomplete base net specification because the tables are still missing. If you don't have access to the tables, is it possible that maybe they pick tables where x, y, and z, where x and z are independent? Yes, it is possible to pick tables where x and z are independent, even for this kind of structure. All right, if you made y 50-50, let's say, positive or negative, independent of whatever x is, and you make z 50-50, positive or negative, independent of what y is, then now effectively you have a distribution where all variables are independent. It's kind of a weird choice of base net structure to encode that distribution, because you could have encoded it with a base net structure with just 3 separate nodes, but somebody could be choosing, for whatever reason, probably not a good reason, a base net that looks like this, but nevertheless the underlying distribution has all variables independent. Right. It's in some sense a poor choice, but it's important to keep in mind that by just looking at the structure, you cannot prove that there is a guaranteed dependence, because you don't know the tables, and the tables could happen to be such that there is no dependence, even though the structure might intuitively suggest there likely is one. Okay, so deseparation is going to be our way of, so the important thing to keep in mind is that by just looking at the structure, from what I just said, we can never say anything about guaranteed dependencies. Like whenever we give you a graph and we say, can you guarantee a dependence between these variables? Unless we give you tables, you cannot guarantee that. The reverse will be true, and the reverse is what we'll look at during lecture. The reverse is, if you're given a graph, but not the tables, it is possible to pinpoint conditional independencies that are guaranteed to be true, no matter what table somebody then adds on to the graph to complete the base net. And we'll do that with deseparation. What we'll do is we'll study the independence properties for just base nets with 3 variables. Then we'll see how we can analyze more complex cases by reducing it to studying the cases of base nets with just 3 variables. And that effectively will be the deseparation algorithm that then will allow us to answer questions about, given a base net, which conditional independencies can we guarantee even without having access to the tables. All right, so here's a first base net with 3 variables. Our example here could be pressure, low pressure could influence whether there is rain or not, could influence whether there is traffic or not. By definition of base nets, this is the expression for the full joint distribution, expressed as a product of the conditionals available at each variable node. This is a causal chain. This is our name for this type of 3-node base net, where we have 3 things that kind of seem to, in some sense, temporarily maybe influence each other. Okay, first question. Are X and Z guaranteed to be independent? No, we already discussed that on the previous slide. Next question we'll ask. So we discussed on the previous slide, we saw an example. In numbers, if you want to make this explicit, this is the example I gave on the previous slide. You just make everything deterministic, and then clearly you're going to have those dependencies, and now they're not independent. So we covered that. Now, how about the other question that we could ask about X and Z? Are they independent given Y? Okay. So the question is, can we, when we start with Z given X and Y, can we somehow rewrite it using the fact that we have this thing over here as just Z given Y, and X disappears? Well, we can do some mathematics using the expressions we have here. We fill in this thing, then we do some simplification, and we're left with just Z given Y. So we just showed that Z is independent of X given Y. We actually also know that's one of the assumptions we make to start out with. We proved it from the expression we have. We could also have said, when you go from chain rule to base net expression, you're already assuming that Z is independent of X given Y, so we don't even need to prove it again. Either way is fine. We now know Z is independent of X given Y. This is true for every such triple. It doesn't matter what the conditional probability table entries are. Whatever numbers you put there, Z will be independent of X given Y. Okay? So intuitively, knowing what's in the middle here blocks the influence from the first variable onto the last variable, and so the first variable becomes irrelevant in terms of finding out more about the last variable. So that's our first example. We'll do 2 more of these, then we'll have our building blocks in place. So next one, common cause. What we have here is our example, a project could be due. That's our Y variable. This could cause the forums to be busy or not busy. This could cause labs to be full or not full. What the joint looks like is given over here. That's by definition of our base net what the joint distribution is. We can now ask again the question. We'll always be asking questions about the 2 outer variables. So in this case again, X and Z. Are X and Z independent? That's one question we can ask. The answer is no, intuitively. Why? Because when a project is due, that will increase the forums being busy, might increase the labs being full, assuming labs is where people work on projects. And so if you know something about forums being busy, that tells you something about the labs being full or not, because forums being busy means that likely projects are due, which in turn means that likely labs are fuller than usual. And so there's no independence guaranteed between X and Z. Note that I'm asking this question very specifically here. I'm asking, given this base net structure, we don't even know the entries in the tables, is it guaranteed that X and Z are independent? And the answer is no, we cannot guarantee that. Could you come up with entries in tables, where a structure like this with the right entries would have X and Z independent? Yes, you could. All right, there are very special choices for the conditional probability tables where they will be independent. In fact, the same choice I mentioned earlier, just make every entry in each table 1/2, assuming they're all binary variables. Then effectively, you have a distribution that's like all independent coin flips. Everything is independent. So if you doctor the distribution at each variable just right, you can have independence. But can we guarantee independence between X and Z from just knowing this structure? No, and in general it won't be true. Yes?
So in general, is it legal to draw an edge connecting two variables that are independent?
So is it legal? So it's a good question. And sometimes you're getting at, if I specified this base net and in every entry I put 1/2, really the fair way for me to represent that distribution to you would have been to just draw 3 separate variables with no edges. That's correct. Some sense drawing anything else in that case would be confusing for no good reason really, except maybe for to trick somebody. Is it legal to draw it this way? I mean, nobody can like tell you you're not allowed to do this. It's just confusing. It's bad practice. But from a mathematical point of view, it's good to understand that it is possible. If you have a base net that looks like this, the tables could be such that everything is actually independent. So from a mathematical point of view, it's good to understand that effectively a base net like this can also represent distributions that are much simpler than the ones that it would typically encode.
Okay, so then the lack of an edge means that they're conditionally independent, but an edge comes with no guarantee that they're...
Exactly. The intuition is exactly that the lack of an edge denotes a commitment to some independences, but the presence of an edge denotes no commitment whatsoever, at least not mathematically, to a dependence. Okay, so how can we show that this is not guaranteed, this independence? Well, all we need to do is to come up with a story and then hopefully instantiate it into a set of numbers that X and Z are dependent for that story / set of numbers. So we can just look at the story here, project, forum, lab. We can think through that when projects are due causes both of them to be busy and full. So as a consequence, knowing something about one tells you something about the other. Putting it in numbers, here's a set of numbers that you can put in the tables. And then if you work out the math, you'll see that P of X comma Z is not equal to Px times Pz. Okay. So now the other question about X and Z is whether they are conditionally independent given Y. The answer here intuitively is going to be yes, because of this cause for both of them. Once you know the cause, knowing about the other consequence being true or false doesn't really affect the first one. So we can try to prove this again. We're interested in this case in Z given X comma Y. We want to try to prove that it's equal to Z given just Y. So first step is just using definition of conditional probability. Now we have the full joint theory of our X, Y, and Z. We can fill in this equation, applying our assumptions we're making about the distribution. Once we fill that in, things simplify. And indeed, we have that Z given X comma Y is equal to just Z given Y. And we proved that for any base net with this structure, no matter what numbers you put in the conditional probability tables, Z will be independent of X given Y. All right. So, intuitively, the common cause, once you observe it, blocks the influence, the flow of information that you might get from other effects for the current effect that you're considering. Last one to consider, common effect. So the example here is, let's assume it could rain or not, there could be a ball game or not. In turn, as a consequence, there could be traffic or not, where both rain and ball game might increase the amount of traffic you get. First question, are the outer variables x and y independent? Over there.
Not really, because rain can cancel the ball game.
Rain can cancel the ball game, absolutely. So that's where it becomes important to start looking at the base net itself and look. So in the real world, they might not be independent. In this base net, are they independent or not?
They are.
This base net, they are. Why? Well, we can just refer back to how we define base nets actually. We start with, if we have a linearization x, y, z, start with x, make no assumptions, then we'll go to y. We replace y given x by just py with this structure, and so that means we assume p of y given x equals just py, which means x and y are independent. Okay? So we already proved it verbally. Now, how about are x and y independent given z? Any thoughts there? I'm going to claim they're not guaranteed to be independent given z. Here's the story version of that. Let's assume that rain and ball game indeed are independent as denoted in the base net. Each of them will influence whether there is high traffic than low traffic. Now, traffic can only be high or low in this space net. Those are the two possibilities. Let's say the first variable you observe is traffic, and you observe that traffic is high. You start thinking about the unobserved variables, rain and ball game. Say, well, traffic is high. Things that tend to cause traffic to become high are rain and ball game. So now the probability of rain and the probability of ball game will have gone up compared to what they were before when I didn't know there was high traffic. So observing high traffic made the probability of rain and the probability of ball game go up. Now next, I'm told it's raining. Okay. Now, I just thought, well, traffic is high. This means likely there must be some rain or a ball game or both, because that's what tends to make traffic high. But now I know it's raining. As a consequence, I'll say, well, now it's less likely there's a ball game. Why? I now have an explanation. Rain explains for me why there is high traffic. I don't need to rely on the ball game as a cause anymore to get the result of high traffic. Rain is already causing that for me, most likely. Not guaranteed. It could be that in addition there is a ball game, which would further improve the probability of high traffic. But in the intermediate stage, where I just knew it was high traffic, there were two possible causes for this high traffic. And now that I know one of them is true, it's much less important that the other one is true to have result in the observation I have. So the probability of ball game actually dropped once I also observed it's raining. Which means that even though I already knew there was traffic, when I then found out it was raining, it still influenced my probability of ball game. And so that means x and y are not conditionally independent given z, because once I already know z, finding out x does still tell me something about y. So the answer here is no. To prove this, all you really have to do is fill in some numbers in these conditional probability tables, and then just look at the probability of y given z, y given x and z, and see that they're actually not the same, and then you've shown there's no such conditional independence. Question?
So I thought that the lack of an arrow between two nodes implies implies that those two variables are conditionally independent?
So that's a good question. Does the lack of an arrow between two nodes imply they're conditionally independent? No. So what we've seen so far, and we'll summarize it on the next slide. So let's start looking at that. So what we're going to look at is the general question: are two variables independent given some evidence by just looking at the graph? And it's not as simple as just looking whether there is an edge or not. It's more complicated than that. But what we will see is that the three cases we just covered are enough to understand all cases. Okay, so the recipe we'll look at is effectively reachability, but with a little bit of a twist. So let's look at a graph, and we'll try to figure out whether there are conditional dependencies by just looking at the graph. The first attempt, which is the one that I suggested here, is if two nodes are connected by a path and not blocked by a shaded node, one that's observed, they are conditionally independent. That'd be a simple attempt. Well, there's a path in the graph, so whenever that path is blocked by an observation, things become conditionally independent. That might be the natural thing to think, but it's actually not the answer. It's almost, but not entirely. The reason it's not entirely the answer is that third example we just looked at. In that third example, observing the node at the bottom actually activated the influence between the two other variables, right? So that's where it breaks. So we need something a little more subtle. This V structure, which is again shown over here, this is what we call a V structure, acts very differently than the other structures we've looked at. In a V structure, when you don't observe the middle node, they're independent. But then when you do observe the middle node, all of a sudden, there could be a dependence. Okay, so that's a little catch there, why we cannot just look at reachability in the graph, where we block things by observations, but sometimes an observation will block things, sometimes an observation will actually enable influence. So here's the catalog that we need to look at. There are active triples and inactive triples. The first column here are the active triples. So what are the possibilities? When you have three variables, you could have a causal chain, that's the first one. If the middle node is not observed, this is an active triple. We could have a common cause. If the middle node is not observed, we have an active triple. We could have a V structure, the common effect. If the middle node is observed, this triple is active. So it's the other way around. The shading indicates observed. And then there's actually a slight variant of that we didn't cover in detail, but it's effectively the same thing. If you have a V structure, but somewhere down the line, and there could be many nodes in between here, something is observed, that's enough to also make that an active triple. The same kind of reasoning holds true as we had for just the V structure triple, because you could imagine that going down that path, if everything is just deterministic, it's the same as observing the variable that's already sitting there. So there you have an example of how things get activated, and so you cannot guarantee independence. These here are the inactive triples. If you have a causal chain with the middle one observed, triple is inactive. Common cause with the middle one observed, triple is inactive. If you have a V structure with this one not observed and also nothing underneath observed, you have an inactive triple. What do I mean with active triple or inactive triple? When I say active triple, what that means is that the two outer variables could influence each other. With an inactive triple, what that means is the two outer variables could not influence each other. Okay? Another way to say it is that for an active triple, we cannot guarantee independence, conditional independence of the outer variables given whatever the evidence is. For an inactive triple, we can guarantee. Here we can guarantee that no matter what the tables are, the two outer variables will be independent given whatever evidence is available to us. Now, once we know what our active triple and inactive triple categorization is, we can start thinking about longer paths. A path is active if each triple is active. So we can look at a graph, some variables observed, some not observed. We want to know for two variables, are they conditional independent? Given the ones that are observed, we can consider all paths between those two variables. For each path, we can check whether the path is active or not. How do we check whether a path is active? We check every triple along that path and see if each triple is active. If each triple is active, the path is active. If one of the triples along the path is not active, that blocks the influence along that path, and that path is inactive. Now, when we're interested in looking at conditional independence between variables, we'll essentially look at all paths between them. And the question becomes, does there exist a active path? If there is an active path or more than one active path, then there could be influence running between them. We cannot guarantee anything. If, however, we consider every single path between them, and every single path between them is inactive, then we know no influence can run between those variables with the current observations. And we know that those variables are guaranteed conditionally independent given the evidence. All right? So we would get a query, are xi and xj independent given some evidence variables? We would check all paths between xi and xj, ignoring directions of edges, any path between xi and xj. If one or more is active, independence cannot be guaranteed, so we cannot guarantee the independence. It could still be there. Somebody could have picked tables that make them independent, but just from looking at the structure, we cannot guarantee anything about independence. If all paths are inactive, then we can make the guarantee. All right, so since we're a little short on time, let's take a really short break here, and then let's work through the examples for the remainder of lecture. All right, let's restart. First example, 4-node base net. Is R independent of B? What do we think? Yes, we think it's independent. They're independent. How do we show this with the D-separation algorithm? We look at all paths between R and B. There is only one path. This path has only one triple on it. Let's check that one triple. It's a V structure. There is no evidence at the bottom of the V structure or in any of its successors down further below. So this V structure triple is inactive. An inactive triple makes the path it's in inactive. So the one path between R and B is inactive, so we are guaranteed independence. How about R independent of B given T? So I hear a no, T is observed. Still only one path between R and B. That one path has only one triple, RTB. That triple is an active triple. It's the one triple along the path, so the entire path is active, which means influence could run between R and B when T is observed. So no, we cannot guarantee that R and B are independent given T. And typically they will be not, but as I said, you never know if somebody picks a special choice of tables. Could always be. Next one, are R and B independent given T prime? I'm hearing no. Why? Well, we have only one path still between R and B. Has only one triple. It's a V structure. It has evidence somewhere along the way, further down below, which means that V structure is a active triple. It's the only triple on the path. So all triples on the path are active. So the path is active. So there could be influence running between R and B given T prime. So we cannot guarantee this conditional independence. All right, a bigger graph. How about, is L independent of T prime given T? So T is the one that's observed, L is here, T prime is over here. Is this conditional independence guaranteed to be true? I'm hearing a yes. Why? Well, there's only one path. That one path has actually two triples along it. It has the LRT triple, and it has the RTT prime triple. Notice here that there's quite a bit of overlap between those triples. And that's how you're supposed to check all triples along a path. You see there is LRT and then RTT prime. And essentially, we want every node that we can take as a middle node of a triple also consider as a middle node of a triple along a path. Now, we need to consider both of those triples and see if they're active or not. Let's first consider the bottom one, RTT prime. That's a causal chain, middle node observed, makes it inactive. Once we have an inactive path, an inactive triple on a path, the path is inactive, so we don't even need to check the other triple. Now, if we were to check the other triple, you might wonder, what's the influence of this being observed on whether that other triple is active or not? Never in our examples where we looked at triples, did we look at what happens when one of the outer nodes is observed. It doesn't matter what the outer nodes do. When we catalog them as active or inactive, the only thing that matters for the categorization is whether the inner node is the one that's observed or not observed. So if we were to look at this, this still would be a causal chain with the middle node not observed, so active, independent of whatever is happening in this outer node here. So that first triple is active, but the second one is not active, so the path is not active, which means the only path is not active, and so this conditional independence is guaranteed to be true. Next one. What we have here is, are L and B independent? I'm hearing yes. Why? There's only one path between them. Let's check that path. If our hunch is that they are independent, we should see if we can track down a triple that's inactive along that path, because once we track down one triple that's inactive along a path, the path is inactive. And so let's start with this triple here. That's a triple along that path. That's an inactive triple. And so the path is inactive, and we can, in this case, guarantee independence between L and B. How about L and B given T? No. Why? Well, there's still only one path. The first triple along the path, this one here, is active. The second triple, this one here, is a causal chain, middle node, not observed, so also active. Again, doesn't matter what the outer nodes do to decide whether a triple is active or inactive. So both triples are active, making the path active, and so there could be influence between L and B once T is observed. How about when T prime is observed? Same thing, right? Because it's the same variables we care about, same path, and now instead of observing T itself, we observe some successor which has the same effect on that triple. It makes that V structure triple active just like it was before, and so there could be influence between L and B. How about L and B given T and R? So T is over here, R over here. How about now? And see some yeses. Okay, let's check this. There's still only this one path. If the intuition is yes, let's see if we can track down a triple along that path that's inactive, because that would make the path inactive. Let's start with this triple. Causal chain, middle node observed, makes it inactive, means the path becomes inactive. It's the only path, so all paths are inactive. So this independence is guaranteed to be true, no matter what people put in their conditional probability tables for this base net. Okay. Now let's look at one where there could be multiple paths between variables. Okay? So, first one, T and D. Are they independent? Can we guarantee that? Just from looking at the structure. Hearing a no. Okay, so, well, let's see. There are two paths. a path on top, path along the bottom. Let's first look at the bottom path. Only one triple along that path. V structure, middle node, not observed, no successors of the middle node observed. So this V structure is inactive. This is an inactive path. Well, find an inactive path is not enough. We actually need to show all paths are inactive if we want to show the independence to be guaranteed to be true. So let's keep going. Let's look at the other one. This is a common cause, middle node not observed, which means it's active. The only triple along that path is active, which means this path is active. Once we find one active path, influence could run between the two variables, so we cannot guarantee this independence. Next one, T independent of D given R. So once this node is observed, seeing some yeses. Why? Well, we already analyzed essentially the same thing. We already analyzed the bottom one. We know this is inactive. The second path here is now also inactive because the middle node has been observed. Only the triple along the path is inactive, makes the path inactive. Both paths between the two variables are inactive, which means no influence can run between those two variables. No matter what numbers you put in the conditional probability tables, we will have that this is true about the distribution defined by that Bayes net. How about if we also observe S? Now, all of a sudden, this bottom path here becomes active. We have an active path between the two variables, and so we cannot guarantee this conditional independence to be true just from the structure of this graph. Okay, so what we've looked at in this lecture is implications of Bayes net structure. We now have an algorithm called d-separation that allows us to read out conditional independencies that are guaranteed to be true no matter what numbers are put in the tables. Okay? Principle, we could look at all pairs of variables and then all subsets of other variables. This would be a lot of things to look at, but we could do that in principle and run d-separation to check whether a pair of variables is independent given that subset of other variables. And we can compile a huge list of conditional independencies that are guaranteed to be true for any Bayes net distribution built around specific Bayes net structure. Okay? So let's start doing that, right? Let's look at some Bayes nets and determine all independencies that are there. First one here. What is the list of all conditional independencies that are true for this Bayes net structure? Well, we have x independent of z given y, and it turns out that's everything. There's nothing else that d-separation or any kind of calculation can give you beyond that. How about the next one? This is the causal chain. Well, the only thing we can guarantee here is that x is independent of z given y. How about the next one, the common cause? We analyze that. The only thing we can guarantee is that x is independent of z. So these are our sets of conditional independency. Whoa, what just happened? Our sets of conditional independencies. Now how about the last one? What's going on there? This is what we call a fully connected Bayes net. What I mean with that, it means that if you look at the linearization here, there's only one linearization, just the way this diag is set up. And any variable we look at, its parents are all the preceding variables in the linearization, which means we made no assumptions. We never reduced the set of variables we condition on. We made no assumptions. Nothing here, empty set. So we can start thinking about what's going on here, right? We're seeing that for the last one we made no assumptions. What that means is that a basenet of this structure over 3 variables x, y, and z can encode any full joint distribution over 3 variables. Because we're not making any assumptions, we're not limiting the type of distribution we can represent. Basenet of this structure can only represent distributions where this property is true. So if I give you a distribution, you can check numerically for the full joint distribution, is this property true? If it's true, then you can say, well, now I can represent this full joint distribution you gave me by this structured basenet. If that property is not true, you cannot use a basenet of that structure to represent that original distribution. Same thing for next one here, the causal chain. If I give you a full joint distribution, you could then, in that full joint distribution, check by doing some numerical calculations whether x is independent of z given y. If you find that's indeed true, that means that full joint distribution can be represented instead of by that full table by a basenet of this structure. If that property is not true, a basenet of this structure will not be able to represent that distribution. And then same reasoning for the last one here. So what this is saying is that for arbitrary full joint distributions, if the properties on the right here are satisfied, the corresponding basenet on the left could be used to represent that distribution. One interesting thing here is that actually these two are the same set, right? What that means is that a full joint distribution that you are able to represent by this basenet here, you are also able to represent by this basenet here and the other way around. In terms of representational capability, meaning which distributions they can represent, they are equivalent. Also meaning that if somebody gave you a basenet in this form over here, you could build that basenet in principle into a full joint table, and then from that full joint table, build out a basenet of this alternative structure and still represent the exact same distribution. Now you might still prefer one over the other because maybe it's easier, because the physical process is a common cause process or a causal chain process, easier to come up with the numbers that you need for one structure than the numbers you need for the other structure. But in terms of representational capabilities, the joint distributions they can represent, these two are actually equivalent. So you can actually start graphing this out. You could essentially think of this case, a simple picture, but you could say, I'm gonna, for every distribution over 3 variables, I'm gonna say that's a point in some space, right? It's not gonna be in 2D space, right? A distribution over 3 variables, if they're binary, you need to specify 2 to the 3 entries, so that's really 8 variables. So you can think of this as some sketch of 8-dimensional space. In 8-dimensional space, then each point, assuming the numbers sum to 1 and are positive, represents a full joint distribution. And some of these points will correspond to distributions that satisfy no conditional independence properties at all. Those will be most of them, because if you generically specify some numbers, it'd be quite a coincidence for any of those conditional independence equations to be true. And these could be represented by a basenet of any of those 6 structures. They're all equivalent. All 6 of those encode making no assumptions about independencies between those variables. Now, if your variables are completely independent, it turns out you can also represent those distributions with a basenet of this type. You can still represent those distributions with a basenet that's fully connected, but the natural thing to do if you were aware of this would be to pick the basenet where they're disconnected, because then the basenet structure would communicate something about the distribution. And then there are intermediate ones where we have just x independent of z given y. We also saw that there was another type, the v structure, that would lie yet somewhere else in this graph, and so forth. But it's important to start understanding the bigger picture here, that there's this set of all possible distributions over 3 variables in this case, and you can start slicing that set and finding subsets that are representable by certain base nets, and that the fully connected one can represent everything. The fully independent one can represent the least in some sense, and the number of points in that set that lie here that have full independence is much, much smaller than the number of points that lie in the set that allows you to represent all distributions. And then there are some intermediaries. Okay. Any questions about this representation? Okay. Then, in summary, what we've seen for basenets is that basenets can compactly encode joint distributions. In fact, sometimes not so compactly. If you use a fully connected basenet, it's not any more compact than your full joint distribution. Naturally so, because you can still represent any full joint distribution. But once you're willing to make assumptions, reduce the size of the parent sets, then you cannot represent any distribution anymore, but maybe still interesting distributions you care about, and you can represent them more compactly. There are guaranteed conditional independencies that you can read off from just the graph structure. The way you do that is with d-separation, which can tell you all the conditional independencies that are guaranteed from just the graph structure. Could there be more conditional independencies than the graph structure encodes? Yes, right? For a very special choice of the entries, for example, all uniform distributions, everything equally likely, then you have full independence no matter what your graph structure is. So keep that in mind. That could be present, could not be present. You don't know what's in addition implied by the tables if you don't have the tables. Where does that put us? We now understand how to represent a distribution as a basenet. We understand what the independencies that are implied by it. The next few lectures we'll start looking at how we can efficiently compute answers to probabilistic inference queries without having to first go back to the full joint distribution and do inference by enumeration. And then after that, we'll look at how instead of encoding those basenets by hand, we can learn them from data. That's it for today. Good luck with your midterm 1 on Monday.